Okay, I'd like to demonstrate how to build a cam mechanism like one used in an EMAT lecture. To do this, I load an image of the assignment itself via the settings under background image, so we can take a better look at it. I want to do this dynamically, meaning place it dynamically on the screen, and I'd like to select this cam mechanism here. I prepared the image before by taking a screenshot. Here you can see roughly what we are dealing with. We can see the cam mechanism in its basic configuration. The cam rotates counterclockwise, which is mathematically the positive direction. The swing angle of the second rocker arm is shown in the mathematically negative direction. Here we have the motion law that should initially be satisfied, or the prescribed motion, however you want to call it. The points, I want to go from a lift angle of 0 degrees, which is the base, to a degree of 60 degrees. CH goes to 60 degrees after one period, which in this case corresponds to 60 degrees. Then it continues to 120 degrees, 120 degrees, and then another 60 degrees further, and that brings us up to 180 degrees, so right in the middle of the two, up to 360 degrees. And then we have another 120 degrees, and then 60 degrees. So we have two dwell phases in this range. Alright. To do this, I'll switch to the quick construction mode and first create a frame, roughly like the one shown here, and then attach this rocker here. Now, this rocker has to perform certain motions, and I want to generate those using this motion graph. So I add a drive and select motion specification without load. So this blue arrow indicates the drive we just added. Let's see what we can do. If we click on modify motion function, we can enter this area here and we can see what is defined. I go a bit deeper into the menu and arrange things slightly. We currently have 1, 2, 3 points, but we actually need 1, 2, 3, 4, 5 points. So I need to insert another point somewhere. I can add a new point here, then we have 1, 2, 3, 4. And here I also need a point, so I'll insert another one, and I've placed it here for now. Let's leave the first point at 0 degrees. That's our reference. Based on this line, in this assembled position, this would correspond to 0 degrees. At this position, we want a lift of 60 degrees. Now the lift is rotated by 60 degrees in this direction. So in this direction it is considered positive. However, in this case we are not in the positive direction, so mathematically we have to assign it as negative. That means I can define this point here. It will occur when this reaches 360 degrees. And here you can see the values are in seconds. Let's assume, for simplicity, 1 revolution per second as an example. Then 120 degrees would correspond to about 0.33 seconds, so 0.3333 seconds, and the second point will be at negative 60 degrees. That would be the motion specification for this. Now, what I still want to do, I'll undo that. For now, I want to define straight lines, so a line, a line, a line. I want the segments to be connected only by lines. Line here as well. And this segment also as a line. Now this point has reached the top, but I don't want it here. I want it at 0.5, which is correct because that corresponds to 180 degrees. But in this region we are also still at negative 60 degrees. Now we can see it a bit more clearly and accurately. I'm also not satisfied with this point yet. it shouldn't be at 0.7 or something like that, but at 0.6667, 2/3 of the period. And here we are back at 0. Now I've defined my motion specification here. Next I want to apply motion laws. I choose a 50-degree polynomial, which is specified here. And I also select a segment type of 50-degree polynomial. These are now my motion definitions. We know that a chem mechanism operates between these elements. Here there's a quick construction mode for the chem mechanisms, which I can use to generate one. I simply click on the first joint and then on the second joint, and the chem profile appears. Then I switch back to the quick construction mode. And if I run the simulation now, it looks like this. Actually, it should also be filled here. I'm not sure why. Oh, now it works. I'm not sure what the issue was before. Normally these chem profiles are also displayed in blue. It seems the software just was a bit slow with its calculation. Now I can move along here and see how the chem disk changes depending on the position, but the motion function itself remains the same. The prescribed motion stays unchanged. From this angle I move 60 degrees within 1 second and keep the dwell phases. That's just a simple example shown here.